Hello, my name is Pablo Ramos. Hello, my name is Pablo Ramos, and I will talk about involutions, as a somewhat lesser known group of permutation matrices. And I will then talk about some applications that they have in the field of crystallography. So the first thing is, what is a permutation matrix? You can see them as, in the simplest way, as operations that take elements in one set, rearrange them. It's essentially a mapping from one set onto itself, so long as it is not an empty set. And you can visualize them as operating over vectors that have all the set elements. So in this case, you have the elements A, B, and C, and an operation can be making B and C trade places with each other, as shown here. Also, permutation matrices, this is how you note them. So they will rearrange the elements of size n, and if so, the matrix needs to be an n by n square matrix. And thus, in this example, performing this multiplication will yield the vector b, a, and c, which is equivalent to the previous operation. Now, it is important to note that every single one of these matrices will have only ones and zeros, and the ones and the zeros will, the ones will never share row and columns with another one. And in the case of permutation matrices where you have cycles of two, or rather involution permutation matrices, the way you have the only way that they can actually have cycles of two. So essentially, permutation matrix can only be an involution if it is not the identity, but it's rather the proper square of the identity shown here in this property. The way that happens is, if I have any number of elements, only two can trade place with each other and maybe one will stay fixed. Or if I have four elements, these two can be trading places. Or I can have other two elements trade places. But the one thing that cannot happen is having three elements, because this would yield a cycle of three, and then it would not be a proper square. Um, so the way those matrices end up looking like, if you actually map these, is they'll always be symmetrical around this this axis right here. So if the ones remain in this symmetrical axis, then those would be fixed elements. But if the ones end up being somewhat opposed to each other, so along this axis, then they will be elements that will be trading places. Rather this b0 and this b0. Um, so yeah, essentially there'll always be symmetry along this line. And the way it looks in terms of rearranging the elements is, if you have n elements here, you will start finding all the possible ways to make these pairs trade places. And you can name these k, the k pairs, or rather the k elements that will form different pairs, and everything else will be fixed. So these pairs here, they will not be trading places. This would be n minus k. And at first you only consider this pair, and then you will consider this other two, and then you will continue to consider every element until you cover as many as possible. And if you do this, you can consider every possible involution. So if you want to know any set of size n, where all the possible involution matrices, what's the number of them? Then this is what you would need to do. Now the way this looks like, the way you would actually calculate it is through this formula. The proper term for these would be all the involutions of a symmetric group. And then the formula looks quite complicated, but if you break it down, it's essentially doing what we've done to this example here. So you begin at k0. This would mean every element is fixed. This is the equivalent of the identity matrix, but we're not interested in that. And then we would go up until n halves. Why n halves? Well, because we're actually considering pairs, not every element So we would be finding all the possible ways that these pairs can be rearranged. Which is why it would be equivalent as stopping here at n halves. But that's because we're considering just the pairs. And then this term here, this is actually the Q binomial coefficient, which represents exactly these. So every time you compute this, you take a value of k and find all the possible states for these pairs. So whether you swap them or not, which is exactly why it's a binomial coefficient. And this term right here, well, this takes into account that the term on the left will give you twice as many answers because it will consider taking an element A and an element B, swapping places as different from B and A trading places. So you'll get twice as many answers. So what you need to do is every time you compute this, you need to divide by 2. And then you divide by 2 again, and then you essentially end up doing it 1/2 to the k times. Yes. So this is the formula. This is how you know how many involution matrices you can have for any set of size n. And if you want to compute it with using, say, Python, well, a summation is just a for loop. So all you need to do is for every k in the range, starting at 0 and then ending in n halves, then you just describe these terms over here. So you have n factorial, which is right here. Then n minus 2k factorial, which is right here. And k factorial, this accounts for the Q binomial coefficient. And then our little correction of dividing by 2 to the k. And naturally, because we ended up starting at 0 to keep the original formula intact, we just subtract one answer, which will be, of course, the identity matrix. But that's a trivial one, so we're not interested in that. Over here, you will see some value correction. So just making sure that the code doesn't take values that are negative or are way too large. Now, let's talk about some practical applications that ACE also can have. So crystallography is the study of materials that exhibit crystalline properties. They can be inorganic, but it can also be organic materials. And essentially, what this means is that their molecular structure will have repeating patterns. So this crystal will iterate itself over the whole structure of the material. One good example is proteins. So as you can see, these structures can be incredibly complex, like in biology. As you can see, this paper here, rather this scientist here shows this this example of a protein and how it can look. Computer graphics enable to be able to rotate this and find different points of view for this protein. You would actually need permutation matrices, or rather lots of matrices that you see as linear transformations that can rotate this around. And we will see how this works in a second. But rather, we're going to use a simpler example, which is titanium dioxide. For instance, consider this polymorph, or rather this the way of arranging its molecular structure. It's called rutile. Crystals have special kinds of axes that are relative to how these structures grow. In this case, the C-axis refers to the lung, to where the crystal grows, kind of like. And if you consider this permutation matrix, if you model this into a vector space and then multiply the whole vector space, so use the linear transformation with this permutation matrix. This was one of the solutions that we found, by the way. If we did this would rotate the whole structure 90 degrees about this axis. So in terms of computer graphics, you could find a different point of view and maybe look at the structure differently to get some insights. But also, you don't necessarily need to restrict yourself to these. If you include negative values, for instance, this would be a mirrored reflection, which would give you potentially it could give you an isomer of certain molecules. So if this is the crystal, then and this is the XY plane, then you can get a mirror image, which may or may not be equivalent. And now this all these molecular teeny tiny properties can by virtue of emergence show you in the real scale world, the macro scale, that this crystal will actually grow into very thin filaments and will have very special properties. This study by Wang and collaborators shows that this little filaments here, if synthesized in the right way and coated with a graphene coating, that will have high conductivity and capacitance, and that makes them really good superconductors. Um, Rather supercapacitors, sorry. And this would have real life applications in electronics. So you can see how very simple mathematical problems um, to study three-dimensional space or ways to rearrange elements can have very, very strong implications in the real world. Um, this is the end of my presentation. Thanks for listening in, and that'll be it. Here's my references.